Welcome back to Chris Does Rocks. It's time for our first Intro to Geology lecture. We will be repeating the class structure of an actual college course by doing the 100/1000 level Intro to Science section. It's in every textbook, in every class. You gotta do it. State mandates and such. We'll skip the syllabus section because there's no homework, tests, or grades in this class. If you want to catch everything, just watch all the videos in order. If you want to catch everything in a very confusing manner, watch them out of order. If you just want to watch one thing, hey, just watch one video. Doesn't matter to me. I'm just the guy on your screen. Let's start off with the scientific method. What is the scientific method? It's less a set of rules and more a structure and way of thinking that scientists use to understand phenomena in the world. Also, to start off with, I'm going to say phenomena a lot. It'll be as not a word to me as it is to you by the end of it. So, the scientific method is typically thought of as applied to physical phenomena, but can be applied to social and economic ones just as easily. We start with our first step, find a question. What does that mean? Just look for something in the world you don't understand and want to have a better idea about. This can be, as I said, some physical event, can be a social, can be whatever. Just identify a hole in your knowledge or the knowledge of society and start working on it. Our next step is to make observations. You found something you don't know, so look at it, study it, find out what things you do know and what things are related to it so you can better define what's going on that you're curious about. Step 3, form a hypothesis. A hypothesis being a statement of an idea, a thought, about how a thing works. It's very important in science that this hypothesis be falsifiable, or something that can be proven wrong. This doesn't mean that your idea has to be wrong or even should be, just that it can be proven wrong in some way. For example, let's pretend we're studying gravity for a moment. Our hypothesis might be that objects of varying sizes will be attracted to each other based off of mass, and that since the Earth is a very large mass, any small human scale mass will be attracted down to the Earth. It's falsifiable by a simple method. We will do a test. Now, all science in scientific method involves testing. This can be a logical test where you just create a scenario where if your thing works, then it will, or if your statement is true, then the logic will follow out, everything will remain correct. If it's not, then you will produce illogical results and absurdities that can't happen. More empirical testing involves actually running an experiment and seeing yes it happened, no it didn't happen. For our gravity test, I have a ball, and if our falsifiable statement that things will fall down in gravity is false, the ball will either stay here, move up, somehow float to the left, anything like that. If it falls down, our falsifiable statement still holds. Ball fell down and also bounced out the tripod. I'm probably having a weird camera angle now. But we would, in an actual scientific study, we would analyze this data, run multiple tests, and see whether it holds true, and update the hypothesis as needed. For example, if the ball always fell down, but sometimes at an angle, we would have to adjust our hypothesis for why that happened. If our ball fell at different speeds, we'd have to update our hypothesis. If it just fell straight up even one time, we'd have to throw the whole thing out because our hypothesis proved entirely wrong. But all of these things are still a valid method of advancing scientific knowledge. Now, it's not an official part, but it is a very important one, that you share your results. Why? Because science and human civilization are team sports. It only works when we're all working together. And then we repeat this entire process as needed. Why? Because we found a hole in the knowledge, we learned something, we now have new information and a different shape of hole because there's a little less there, and we keep repeating that process and learning more and more and more ad infinitum. The scientific method never really ends. It just keeps us learning new things. Now, we move on to a rather controversial part for non-scientists and a rather tediously that's obvious for those of us in science: theories and laws of science. So, you may have heard people say, oh, well, whatever, is just a theory. That's because they don't know what theory means in science. A scientific theory is a hypothesis that has been tested repeatedly and has wide acceptance in the scientific community. And it also explains all of the known phenomena related to that theory. This means you can look at it and say, the theory of gravity, we know what happens. The theory of evolution, we know what happens. It isn't necessarily true, it just means that nothing so far has disproved this theory. It's also important that a scientific theory does not have to explain why a thing is happening, or how a thing is happening, what it's going to do. It just has to explain within the scale or the scope of the theory. So, theory of evolution will tell you about how things inherit traits from their parents and populations will change over time. It does not have to explain why some people have one blood type and some people have another and where they came from. It doesn't have to explain the origins of life, it just has to explain how populations change over time. Theory of gravity, explaining about things drawn to each other and things falling in motion based on gravity, but it doesn't have to explain anything about, say, why light will have a maximum speed, what colors are tied to what wavelengths. Any of that is outside of the scope, so the theory of gravity holds because it only applies to a specific thing. Scientific laws, on the other hand, are rules derived from the extensive testing of hypotheses. These rules have either a specifically defined statement or a mathematical expression. Okay, so the gravity is a theory, but motion is described by laws. Specifically, Isaac Newton's 3 laws of motion gave us that an object will move, will continue moving until acted on by an outside rest. An object will not start moving until acted on by an outside force, yada yada yada. These laws have to provide a description of the process, but not the explanation. It doesn't have to tell you how a thing will stop, just that it won't stop until something else happens, and it will continue until that happens. A law has the very specific thing of, it has predictive power. Not necessarily explanations, but it can predict what will happen in the future. So our example of evolution, it can explain what happened in the past, cannot tell you what the next generation is going to look like, or 5, or 10, or 20 generations, or 1,000. It won't tell you what populations will do in the future, just what happened in the past. Laws of motion can't tell you how a thing moves, why it stops, but it can tell you that in a given scenario, here's what the movement will be. So, That's your difference between theory and law. Theory is explanation, if it not perfect. Law is rules and prediction, even if we don't understand them. Alright, so that gives you your two basic scientific, I had to explain this for standards and curriculum requirements. Our next lesson will cover the history of geology and more specifically the concepts of geologic and deep time. So, I guess I'll see you then. There you go.